So today let's explore this failed 120 watt gallium nitride charger donated by a viewer, so big thanks for the donation. This seems like a properly built charger. It's not one of these super cheap fake gallium nitride chargers, but for some reason it failed anyway. So let's find out what failed in it, and also what's inside and how does it work, or used to work actually. Is it the flyback or some other topology of a switching power supply? It has 2 USB-C ports and 1 USB-A port. And the marking, the USB-C ports go up to 20 volts and individually produce 100 watts. The USB-A port just up to 12 volts and 22.5 watts. But the 2 USB-C ports combined, or 3 ports combined, can produce up to 120 watts, which is quite a lot of power for a charger of this size. Let's just try to plug it in. What happens? Let's use this tester, but nothing. That was the USB-A port, now the USB-C ports. There is really nothing to test. No voltage on any of the ports. So the only thing left to do is to open it. Which might not be easy. At least the $1, $2, $3 AliExpress or eBay rubbish is much easier to open than this. I had to cut it from 3 sides before it started opening. It's full of resin. Bloody hell, that's going to be annoying to open. This thing's completely filled solid with some resin. The absolute most welcoming design for anybody trying to fix it or for anybody trying to learn how things work. At least the resin is not very strong. How am I supposed to open it? Of course I know I'm not, but this is not what I'm asking. It's just not possible to pull it out. So I've cut this part of the box off. And that's it. Does it now come out? Still doesn't want to come out. Some shielding here. These are interference shielding layers, I guess. Here are the ports, some electrolytic capacitor, probably polymer, some chips. Are these synchronous rectifiers or the communication chips for the ports, more likely. Here's some optocoupler, and most of it still under the resin. So let's start peeling it. I'll just use its own parts to dissect it. It's better to actually peel it off in bigger chunks. And I will do most of it off camera. This is taking way too long. So finally the pink plague is eradicated, but it was quite a purgatory to get it out. You can see all the components in it on 4 boards from the outside, and some other boards here. This is like a sandwich. Several boards this way, between the 2 main boards here. 4 boards plus 2 boards, plus this small interference suppression board. The mains comes in here. There is some fuse here, the black box. This X capacitor here for interference suppression, some inductors here and here, another inductor here, some bridge rectifier. The 2 AC pins are actually shorted together. I was thinking for a while it's a doubler, but it's not. There is another rectifier here for more current, 2 rectifiers, and each of them working as 2 diodes, or 2 diodes in parallel and the other 2 in parallel, basically, for double the current rating. Here seems to be a diode, ultra-fast diode, probably in the power factor correction. And some film capacitors. The rectifier goes into the film capacitors, not an electrolytic one, so there has to be a power factor correction, which is probably required for 120 watts. Is this the transformer or the power factor correction inductor actually? Some chips here. Here is the optocoupler, quite a lot of it in it. And what the hell is this? It's a ferrite core and the board is going through it. Are the windings of the transformer printed on the board? That's alien technology actually. Is this a synchronous rectifier? The 3 capacitors, polymer capacitors, parallel to the outputs. And here's some temperature sensor sensing the temperature here. A lot of chips. Another optocoupler. Let's measure some components in it. It's not really possible to measure the chips, but at least the simple ones. Here it looks like the bridge rectifier is shorted, but it's actually jumpered to work as 2 diodes only. Here's the power factor correction ultra-fast diode, which seems good. The optocoupler, some transistor in it, or diode. This is the voltage drop of the infrared LED in the optocoupler. You can of course test some capacitors for shorts. not shorted, some diode. The film capacitor is not shorted. The other way, I will see some diode, of course. 2 diodes in a series voltage drop, but not a shorted capacitor. This is an inductor, a tiny piece of ferrite with a conductor going through it, maybe. Another inductor here. Of course, an extremely low voltage drop for DC current from this tester. Some transistor, base 2 collector, base 2 emitter, good NPN transistor. Another transistor, collector to base 2 collector. Is it a MOSFET? Maybe it's a MOSFET. Emitter to collector, or drain to source in case of a MOSFET. This seems shorted. Resistance meter shows just 5 ohms. That's suspicious. This transistor might be actually faulty, or it's something else in parallel to it. There's a transistor. That's something external. Too much voltage drop. Something external again. Source to drain, nothing. Drain to source. An anti-parallel diode, which is part of a MOSFET junction. Drain to source, which would mean it's a P-channel MOSFET, and it's good. What about the polymer capacitors here at the output? It's charging, good. This one, charging, good. This one, hell yes, this one is shorted. Or the other way, again shorted. The other one is the other way. They actually charged the wrong way, and some diode voltage drop stops them from charging further. This is the right way. The right way. The wrong way again. It's charging, and then some diode voltage drop stops it from charging further. So these two are good. And this one is probably shorted, or basically anything else on the supply rail here. And by the way, there is the capacitor between the primary and secondary side, which has to be a safety capacitor, going between one of the mains terminals and this shielding, which then also goes to the negative of the output. Here is the marking of it, 100 picofarads probably. Is it a safety capacitor? It should be a class Y1 capacitor in this position. But I'm digressing. Let's look at the capacitor which is shorted. This seems to be the part of the USB-C output, or some control circuitry around it. Of course, some of the circuitry is common for all outputs, so one shorted capacitor probably disables everything here. This one seems to be shorted, but it also could be anything else on this rail. Some shorted chip here, maybe the control chip is shorted, maybe the synchronous rectifier somewhere on this rail is bad. But of course the question is, how do I even get to it? Do I desolder this board or this one? Maybe this one has less connections to it. This is basically impossible to fix or work on. Of course, I was thinking about cutting the pins of the capacitor off on the board here to verify it's the capacitor shorted, not something else, but this is probably a double-sided board at least, more likely multi-layer board, so cutting it off here doesn't really ensure it's disconnected from everything. Let's try to desolder. There is no way of fixing this, or at least no way of fixing this in a way that it would be still useful. And it's opening now. That's it, separated, except this capacitor. Here's the big electrolytic capacitor after the power factor correction. The space for it here in some insulation. Even more of the pink disaster here. I cleaned this section and you're gonna see some chip here, some small components here, some other temperature sensor, 4.7 microhenry inductors here. Here's the ferrite around the board. This board with some diode here, and the other board. The big capacitor here. A small electrolytic capacitor also here. And this thing doesn't seem to go to the secondary side, so it's probably an inductor. It spins on just one side. So then this has to be the main transformer, doesn't it? It's on a very thick board, much thicker than the other ones. There has to be multiple layers of printed windings basically. But everybody's screaming desolder the shorted capacitor. I checked, it's still shorted after severing this thing in half, but it still could be something else on this side of the thing. The capacitor's out, is it shorted? It's actually charging, it's not shorted. 470 microfarads, 25 volts. The short remains on the board. There are also some SMD ceramic capacitors on this rail. Are these shorted, or some of them? I took 7 SMD ceramic capacitors out of it. Maybe this one wasn't on the rail, but these 6 were, and none of them is shorted. The short is still on the board. What are these things? Synchronous rectifier transistors. Let's smear some heatsink paste, a white one on them. Is there any marking on them? What's even the point of putting invisible markings on components? Nobody sane is ever going to look at anyway. And the datasheet of it. N-channel MOSFET very low on-state resistance optimized for synchronous rectification. 40 volts, 1.8 milliohms. And the markings shorter than the actual full type number. And how does it even produce voltages for 3 ports? There is one power supply which might go into one of them, and the other ones can have some converters, some buck or boost regulator synchronous converters to have different voltages than the first one. Given I can see 2 inductors here. What else these MOSFETs could be other than synchronous buck regulators or boost regulators? A few more here. Or maybe some minimum loads or active discharging of the capacitors? Or are they disconnecting the outputs? A MOSFET disconnecting the output wouldn't explain a shorted rail though. Let's just start removing them and see if the short circuit disappears. I took the plastic part of it off, then I desoldered the rest of it, and the short is still there. It's not this one. The second one, the plastic is gone, desoldering the metal part of it. There is one more ceramic capacitor on the USB-A rail. Is it this one? Still shorted. It's not these MOSFETs. This one or this one. I can see their anti-parallel diode. They are not shorted, and they have enough space around them to probe, unlike these ones, which I had to remove. Let's separate this board from this one to see if the short remains here or here. And I actually measured. The power terminals of this port are also shorted. I was trying to desolder it, but I can actually just... And that's it. The short disappeared from this board and remained on this one. And the separation of this board actually reveals 2 more MOSFETs here. One seems good, I can see it's anti-parallel or source to drain diode. The other one is finally this one, the shorted one. And the marking's the good one. And the one that seems shorted, they seem to be the same type. Another 40 volt N-channel MOSFET, but this one less current rating and more on-state resistance. Let's remove it in the most sophisticated way, of course. It's gone, here you can see its footprint. And probing into it and it's still shorted. What the hell? It wasn't the MOSFET. The pins of the polymer capacitor, this one is still showing short as well. I tested or removed everything that seems to be on this rail. This MOSFET is good, these 3 capacitors, the ceramic ones, these 4, and these 2 MOSFET is good. This one is good. Is the short in some chip here? Or here? Or could it be shorted on these boards? Let's just see. I measured it and the short is still on the main board. Okay, so let's just backfeed current from a power supply into the capacitor location here and watch on a thermal camera what gets hot. Not much happening at 200 milliamps, 500 milliamps, and it's actually showing up. 800 milliamps, 1 amp, and it's bloody obvious. Let's use the macro lens. It's this chip what's getting hot. And of course the board under it. On the other side, but no component here. The power supply is limited to 1 amp, and the voltage here is 1.4 volts, which means the chip is dissipating 1.4 watts. Let's take a look at the marking of the hot chip. The other one is the same type or not? It seems like the same type, but in a different font. And of course the final repair. Here's the empty footprint of the chip, and finally the short is gone from the capacitor location. Now probing it the wrong way, I can see some diode in something, probably in a MOSFET, and the right way, it's open circuit. So the chip was the short circuit. It seems to be a dedicated chip for the communication protocol and the voltage conversion. It communicates with the charged device and negotiates the voltage, but it also controls the gates of MOSFETs in a synchronous buck regulator, senses the current on this current sensing shunt, 5 milliohms, and it can also disconnect the load using this MOSFET or this one for this load. This example shows 2 ports on one chip, but in this charger each of them has its own chip, probably so that each of the ports can have a different voltage. Let's identify the rest of the chips. This one is on the secondary side of the transformer, a chip or a MOSFET. I guess this is actually the synchronous rectification of the main power supply. This is the actual synchronous rectifier MOSFET. The other ones are synchronous buck regulators, or to disconnect the outputs. The charger can go up to 20 volts, and the voltage on the transformer secondary swings at least that much to the other polarity, and the output voltage is adding to this, so the rectification MOSFET would see at least 40 volts, and the 40 volt MOSFETs would have no headroom. This 100 volt MOSFET actually makes much more sense as a synchronous rectifier of the de-isolated power supply. And there is also this thing here. This seems to be a 32-bit microcontroller, with the datasheet only in Chinese, it seems, and having to use this to basically just convert one voltage to another is kind of crazy. But anyway, here's the pinout of it. And the primary side has this chip near the power factor correction. It's a gallium nitride transistor with an integrated gate driver, 700 volt rating, integrated current sensing and over temperature protection. But of course the most important information in the datasheet nowadays is this and this virtue signaling nonsense. But we also get some example schematics and pinouts, and so on. The primary side also has this chip. It's a gallium nitride integrated power stage, a half bridge with isolated gate drivers. And of course it seems odd to use a half bridge for a flyback. And this thing has to be a flyback because on the secondary side there is just one synchronous rectifier MOSFET. But here's some typical application circuit, an active clamp flyback converter. It's basically using one transistor in the half bridge as the switch for the flyback, and the other one is for the active clamping. Normally the transformer leakage inductance energy would go via a diode into a capacitor, and then it would be dissipated in a resistor. This would be a conventional RCD snubber network. But here the leakage inductance energy can go into a capacitor and be recycled instead of dissipated. And here it explains how to drive the gate of these gallium nitride transistors. They're not like MOSFETs. The gate of these ones actually acts as a diode in forward with a voltage drop of about 3 or 4 volts. There has to be a small constant current going through this diode to keep it on. And in the off state they recommend a negative voltage, because the threshold voltage is very low, about 1 volt. Here they're using a steady state resistor to set the steady state current through the diode, and a transient resistor with a series capacitor which basically charges and creates this negative bias for the gate in the off state. And right next to the previous one, finally this chip. And that's actually the control chip of the flyback section, a hybrid flyback controller. Then the power supply topology isn't an active clamp flyback, as the gallium nitride half-bridge datasheet suggested, but a hybrid flyback, which basically has a half-bridge going into the primary of the transformer via a capacitor, so there is no DC going into the primary, unlike a more conventional flyback which just gives it a pulsed DC. But despite the primary is getting AC, the secondary is rectified in just 1/2 cycle. And here's some example waveforms, the gate drive with some dead time, the half-bridge output, and here's the magnetizing current plus the induced current here. And here's the half cycles in the 1/2 cycle rectified secondary. And for very low losses it's using ZVS operation, zero voltage switching. But of course the video is getting bloody long, you can find the datasheet yourself and read it. And these two terminals are the primary of the transformer. One goes via a tiny inductor into the output of the half bridge, and the other one goes into this, which is this capacitor. Series capacitor in a series with the primary, a resonant capacitor. It seems like a polypropylene capacitor, 560 nano, 250 volts. 55 rings on a ring tester with this inductor, way too many for polyester. And ring testing the primary of the transformer to verify it's on these terminals, 18 rings, so these are actually the primary. So we identified all the critical components in it, the gallium nitride half bridge here, and the control chip for it, the gallium nitride switching transistor with its gate driver here, and the control chip might be this. And the last thing to do is the autopsy of this transformer, of course. Let's separate this, if you can even call this a transformer. Is it compatible with my melted hair dryer? It actually worked. The freight core opened and you can see the windings printed on the board inside of the ferrite. Well, you can't actually see them, but you can probably imagine it. This is the secondary. One end of it goes straight through the positive of the capacitor at the output, and the other one probably makes more turns, maybe in the next layer, or several layers. Then it goes via the synchronous rectifier into the negative of the capacitor. And this is the primary side, which probably has the winding on this side. And there had to be some air gap in the core. I guess this is the material filling the gap. Looking at it closer, it seems like it's actually split. maybe one or a couple turns of the secondary was here, one turn of the secondary on the other side, or a couple turns. The primary must have been somewhere in the middle of it. This probably has a lot of layers. Of course, why not cut it and see the cross-sectional view of it? A closer look at it. Even closer. It seems the secondary was two layers, two turns, one layer on top and one at the bottom, and the primary was multiple turns in several layers in between. Next to the primary winding might have been the auxiliary, and the two thin layers might have been some interference shield. So that's a cross-section of a printed transformer. And the same viewer also donated some 18650 cells, so I'm measuring their capacity. One is 1465 mAh, the other yellow cell 1464. And the last donated cell is actually much better. It can actually go into one of my headlamps. And of course, thanks for the donation. This charger was quite intriguing to explore. An interesting design but bloody complex. With so many components, the probability of some failing is adding up. So that's it, and if you like my videos, please consider subscribing, supporting my channel on Patreon or using the thanks button. This was another quite laborious video to make, and this channel couldn't exist without your support. And big thanks to all of you who already support me and keep this channel running.